Good day, everyone. Zen Programmer here. Today, we are going to do something fun with data science. Welcome to our presentation titled Predicting Meme Coin Price Movements with Data Science. We'll be diving deep into the world of meme coins and exploring how we can leverage data science techniques to make sense of their unpredictable price behavior. Meme coins, as many of you know, have become a phenomenon in the crypto world, largely driven by social sentiment and viral trends. I'm happy to guide you through our data-driven approach to forecasting meme coin prices. Please note this document is served as a high-level overview of how to build the data model and many considerations, and investing in cryptocurrency is risky. Do so at your own risk. Meme coins are a unique category in the cryptocurrency market. Unlike established coins like Bitcoin or Ethereum, meme coins often have little intrinsic value and are driven primarily by social media hype and community enthusiasm. Examples like Dogecoin, Shiba Inu, and DOG on Bitcoin have shown explosive growth at times, only to crash just as quickly. The high volatility makes these coins particularly risky, but also potentially lucrative for investors who can anticipate market movements. Our objective was to use data science techniques to develop a model that can forecast price trends and provide actionable insights for traders and investors. We aim to answer a key question. Can we predict meme coin price movements using a combination of market data, social media sentiment, and on-chain analytics? To address this challenge, we designed a robust technology stack. We started with Python for data collection, using APIs like CoinGecko and Binance for price data, and the Twitter API for social sentiment. We also used Scrapy for web scraping Reddit forums, where meme coin discussions are prevalent. For data storage, scalable solutions like AWS S3 and Snowflake were chosen due to the large volume of data we needed to handle. For data processing, we utilized Pandas and NumPy for smaller datasets and Apache Spark for distributed computing when dealing with larger data volumes. Moving on to modeling, we used scikit-learn for traditional machine learning models, while TensorFlow and Keras were employed for deep learning tasks. Hugging Face's NLP models helped us extract sentiment insights from social media data. In deployment, Flask and FastAPI were used to create real-time prediction APIs. We relied on Docker and Kubernetes for containerization and scalability, while AWS Lambda enabled us to implement a serverless architecture. Finally, we monitored model performance using Grafana dashboards. As for the team, we required a multidisciplinary group: data scientists to develop the predictive models, data engineers to manage the pipelines and databases, an NLP specialist for sentiment analysis, and a DevOps engineer to handle deployment and monitoring. The project manager ensured that all components came together smoothly, coordinating tasks and timelines. The goal of our project was to develop a model capable of predicting meme coin price movements. We focused on two main types of predictions: classification, to determine whether the price would go up or down, and regression, to estimate the percentage change in price. This dual approach allowed us to address both short-term trading decisions and longer-term investment strategies. However, there were several challenges. Meme coins are often subject to market manipulation, such as pump-and-dump schemes, which can introduce noise into the data. Additionally, meme coins are highly sensitive to sudden changes in sentiment, such as a tweet from a celebrity like Elon Musk. This made it crucial to incorporate sentiment analysis and on-chain data into our predictive models, rather than relying solely on traditional market indicators. We gathered data from several key sources to create a comprehensive dataset. First, we obtained price and volume data from platforms like CoinGecko, CoinMarketCap, and Binance API. This data provided the historical trends needed for time series analysis. Next, we focused on social media sentiment, as meme coin prices are heavily influenced by online discussions. We collected data from Twitter and Reddit forums, like Crypto Moonshots, where meme coin traders often share their thoughts and hype new projects. We used BERT and Vader models to analyze the sentiment of these posts, determining whether the general mood was positive, negative, or neutral. We also included Google Trends data to measure public interest in specific meme coins. This provided an additional signal for predicting price movements. On-chain data, such as wallet activity and transaction volumes, was obtained from Etherscan and Glassnode, helping us track whale activity and identify potential price manipulation. Finally, we monitored news and influencer mentions to capture the impact of tweets and headlines, particularly those from high-profile figures in the crypto space. After collecting the raw data, we needed to clean and prepare it for modeling. This involved removing duplicates, handling missing values, and filtering out noisy social media text. We created a range of features to enhance our predictive models. For price-based features, we calculated returns, moving averages, Bollinger Bands, and the Relative Strength Index, RSI. These indicators provided insights into market trends and potential reversals. We also engineered sentiment-based features, such as sentiment scores derived from NLP analysis and engagement metrics like the number of likes and retweets on a post. On-chain metrics were another critical component. We looked at whale activity, new wallet creation, and transaction counts to gauge market interest and detect potential manipulation. Lastly, we incorporated Google Trends data, using normalized search interest and shifts in search volume as predictive features. Exploratory data analysis, or EDA, was essential to understand the relationships between our features and the target variable, meme coin price changes. We conducted a correlation analysis to identify the most impactful features such as sentiment scores, trading volume, and whale transactions. We visualized time series data to observe price trends and detect patterns. We also plotted sentiment analysis trends to identify spikes in positive or negative sentiment that could precede price movements. Finally, we analyzed holder distribution, showing the concentration of large wallet holders, or whales, and its impact on market volatility. This analysis confirmed that sentiment and whale trades were strong predictors of price changes. We started with a baseline logistic regression model for classification. While simple, this model provided a good starting point for evaluating the predictive power of our features. We then moved on to more advanced models like Random Forest and XGBoost, which excel at handling mixed feature types and complex interactions. For time series data, we used long short-term memory, LSTM, and gated recurrent unit, GRU, models, which are designed to capture sequential patterns. Additionally, we employed transformer models like BERT for sentiment analysis, leveraging their ability to understand the context of social media posts. We compared the models based on performance metrics, interpretability, and computational efficiency, selecting the best one for each prediction task. Once we selected our models, the next step was training and fine-tuning them. We split the data set into 3 parts: 70% for training, 15% for validation, and 15% for testing. Since meme coin prices follow time-dependent patterns, we use time series cross-validation rather than a random split. This approach ensured that our model was tested on unseen future data, providing a realistic evaluation of its performance. We performed hyperparameter tuning using techniques like grid search and random search. Additionally, we experimented with Bayesian optimization using Optuna to find the optimal set of parameters for each model. This process helped improve the accuracy and robustness of our predictions. For deep learning models, we adjusted parameters like learning rate, batch size, and dropout rates to avoid overfitting. To assess our model's performance, we used a combination of classification and regression metrics. For classification models, we focused on accuracy, precision, recall, and the F1 score. These metrics gave us a balanced view of the model's ability to predict up or down movements correctly. For regression tasks, where we predicted the percentage change in price, we used mean absolute error, MAE, and root mean squared error, RMSE. MAE provides a simple average error magnitude, while RMSE penalizes larger errors, giving us a clearer picture of our model's predictive quality. We also backtested our predictions using financial metrics like the Sharpe ratio and maximum drawdown. This allowed us to simulate how our model would perform in a trading environment and measure its risk-adjusted returns. For instance, if our model had a high precision but a low recall, it might be suitable for cautious trading strategies that prioritize avoiding false positives. Our model evaluation yielded promising results. The best performing model was the XGBoost classifier, which achieved an accuracy of 85% and an F1 score of 0.82. For the regression task, our LSTM model had the lowest RMSE, indicating strong predictive performance in forecasting price changes. One of the key insights from our analysis was the significant impact of sentiment scores on price movement predictions. Using SHAP analysis, we identified that features like sentiment score, trading volume changes, and whale activity were among the most influential. Additionally, our backtesting results showed a potential return of 25% over a 3-month period, using a simple trading strategy based on the model's predictions. This demonstrates the practical application of our approach in real-world trading scenarios. After validating our model's performance, we moved on to deployment. We built an API using Flask and Fast API, allowing users to make real-time predictions by inputting data through a web interface. We containerized our application using Docker, which simplified the deployment process across different environments. To ensure scalability, we used Kubernetes for orchestration, enabling us to handle increasing demand seamlessly. For serverless execution, we implemented parts of our pipeline using AWS Lambda, which reduced costs by running functions only when triggered by new data. We set up real-time monitoring using Grafana dashboards, tracking key metrics such as model accuracy, latency, and API response times. This setup allows us to detect any issues quickly and ensure that our predictions remain reliable. Despite our successes, there were several challenges and limitations we encountered. One major issue was market manipulation, particularly pump and dump schemes. These events can cause sudden, unpredictable price spikes that are difficult for any model to anticipate accurately. Another challenge was data quality. Social media sentiment data often contains noise from bots and fake accounts, which can distort the analysis. We had to implement extensive filtering and pre-processing to mitigate this problem. Overfitting was also a concern, as meme coin data can be highly volatile and specific to certain periods. To address this, we employed techniques like regularization and dropout layers in our deep learning models. Lastly, the generalizability of our model is limited. The model performs well for specific meme coins with high social media activity, but it may struggle to predict price movements for new or less popular coins with little historical data. Looking ahead, there are several ways we can enhance our model. First, integrating real-time data using WebSockets could provide faster updates and improve the responsiveness of our predictions. This would be especially useful for traders who need immediate insights during volatile market conditions. We also plan to experiment with reinforcement learning, which could enable our model to adapt its strategy based on feedback from the market. This approach would allow us to create an adaptive trading bot that learns from both successful and unsuccessful trades. In terms of sentiment analysis, we're considering using larger NLP models like GPT-4 to gain a deeper understanding of social media context and sentiment shifts. These models could help us capture more nuanced sentiment, particularly in meme-driven communities where language is often playful and context-dependent. In summary, our project demonstrates a data-driven approach to predicting meme coin price movements. By combining market data, social sentiment, and on-chain metrics, we developed a model that shows strong predictive capabilities. However, extensive validation testing is crucial to ensure the model's reliability across different market conditions. We plan to incorporate additional testing methods, such as out-of-sample testing and stress testing, to further evaluate its robustness. Risk management is another area of focus. Implementing stop-loss mechanisms and confidence scores can help mitigate potential losses in live trading. From a compliance standpoint, we must also monitor ethical concerns, particularly in detecting and avoiding market manipulation. Finally, we aim to develop a user-friendly dashboard that provides real-time insights and visualizations, making our predictions accessible to both traders and investors. Using cloud solutions like AWS and Google Cloud will ensure the scalability and efficiency of our platform as it grows. Thank you for your time and attention. This is Zen Programmer. We shall see each other next time.